So what do we have on the bench today? Well, it's not tubes or transistors, it's both. A 1960s HP counter with Nixie tubes. Stay tuned to see if I can get this old beast running again. Okay, so the actual model number of HP I'm playing with is the HP 5233L. It's actually a 2-channel counter, up to 5 digits, or I think 2 megacycles it goes up to, all the way down to like 1 cycle a week or something ridiculously slow like that. It's a real pity about most of these old Nixie tube gear stuff. Most of them have been scrapped out long ago for their Nixie tubes. Or people find them nowadays and try to convert them into a clock somehow and destroy them. So it's actually nice to see one that's not been mucked with at all from what I can see in the front. It's of course a little dirty because it was in some guy's lab for a long time. Fortunately it wasn't in a basement lab, it was an upstairs lab, and so it's got no moisture, so it should be nice on the inside. Turning these into clocks, yeah, there's a novelty about it. You see thousands of them on YouTube, but it's really just a pity because it is a very, very nice counter. Fairly accurate. And most importantly, this is going to be a really good learning job because this is the Epoch change from good old vacuum tubes to transistors. Anyway, let me put this down because it's precariously set up there. I went online with a couple of the HP communities and chatted around, and turns out this is a really good learning project. It's got the basic beauty of all the HP, plus it's fairly easy to work on according to the chaps I've chatted with. And I eventually came up with a 25-point plan. I don't know if you can read this, I might attach it somewhere so you can. But it basically tells me how to go through this type of device and get it running again. I could just plug it in right now and not worry about it and just bring it up, but there's always a chance it's going to release the magic smoke and never be usable again. As I've never really worked on a piece of gear this old with transistors and tubes in it at the same time, especially early transistors, the advice I got was quite good. Of course, it's first off, get the schematics, which I have here. Study schematics to no end, we'll go over that. Open it up, inspect for defects, goes on, clean and required, identify and fix any defects, pull cards, and keep everything clean. So basically it's just a recipe for cleaning things up and running it. The main thing is to get the cards out and check the power supply. This has a linear power supply with some wicking big caps in it, and God knows if they're any good. So power supply burn-in to reformat the caps if they're going to reform, and we'll know after a few hours or a few minutes under a dim bulb if the caps have reformed. So that is part of the plan. But now, without further ado, I'm going to go put this big thing away, and we can review the schematic first. Bloody heavy. I did manage to find a copy of the manual, an early copy. This is probably from a very early copy. But unfortunately, it doesn't have a how it works section, so it's kind of hard to figure out what's going on here. It has a good schematic section, but that didn't help me a lot. And it probably didn't help the engineers back in the day either, because this came out in about late 62, early 63. By 1963, the end of 63, they came out with a much better manual, and the principles of operation is actually a longer document than the original manual, excluding the schematic. So, I think it was a simple case of engineers screaming, how does this work, how does this work? And HP basically providing how it works. And it's got all your basic theory in here of digital electronics, which to many modern guys are, or actually anybody who does any modern digital electronics, are very familiar with. Most key to me, as part of the learning process, are these 3 circuits here. Multi-shot vibrator, a trigger, or in this case it's a Schmidt trigger, and a flip-flop. And what I'm going to do next is recreate these 3 circuits on a breadboard. There's always a problem with doing this type of stuff on a breadboard, is they're pretty flaky, but we'll see once I'm done with that. So after I finish off these three, the next I'm going to do is an actual binary counting circuit using flip-flops. And then finally I'm going to put together how the actual display works, the digital display. So let's get right to it. So here's my breadboard with my 3 circuits I'll put in them. I've got here my multi-vibrator, a one-shot multi-vibrator, my Schmitt trigger, and over here I got my flip-flop. I only can run one at once because they tend to interfere with each other. So we'll start with the multi-shot vibrator, and when I press the button, the light goes on for a set period of time. So our next one in the triad is the Schmitt trigger. This is just an input from a signal generator that's generating a pulsating signal with a high and low. Don't stop that. So if I stick that in there, as you can see, bing, 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 sort of goes off randomly. If I take it now and put it on the Schmitt trigger, which is this one over here, it smooths it out. We only get a blinking light, not the little flickers in it, because it's triggering on that and only at the, in this case, in the low points, I think. And then finally we've got our flip-flop over here, and I'll set that one up next. Okay, so our flip-flop is all set up. It's like, of course, binary, off or on, off, whatever which one you want to pick or arbitrarily choose. And when I bring it to ground, it goes off and on, off and on. Real problem with this breadboard is it's really crappy. What I could do now is hook these up so they actually work together. So let me go hook that up now. So I can do a demo here of the Schmitt trigger working with the flip-flop. As you see, it's blinking off and on there. And if I stick that into the flip-flop control, there we go. The flip-flop will sync in unison with that. Flip-flop, flip-flop. So it's actually counting there. In this case, I've got the multi-vibrator hooked into the Schmitt trigger, which will turn the Schmitt trigger on when the multi-vibrator's on, and then it'll flip the flip-flop back and forth. Of course, in this case, it's defaulting to that flip-flop to be on, but that doesn't really matter how you set it up. So if I press the button, there we go. Now the next part of this thing is taking this binary output and building it into the next set of circuits. And of course, you can't count much except 0 or 1 with one flip-flop, but with 4 flip-flops on a board, you can count all the way from 0 to 9. And I'll set this one up now to go. So here I am with my flip-flop circuit all set up. The greens represent 0, the reds represent 1, and the reds are weighted 1, 2, 2, and 4. So with the first pulse, we get 1. Second pulse, we get 2. Third pulse, we get 3. Fourth pulse, we'll get 2 and 2 is 4. The fifth pulse, we'll get 5. And the sixth pulse, we'll get 2 and 4, which is 6. And then it's just one more, it's 7. And then 2, 4, and 4 is 8. And finally one more is 9. And that's basically how a flip-flop counter works. So to do the next part of the circuit, where we take this digital format and get it into the Nixie display, I can't actually show it to you here, but I have to go to the other workbench. I have to go to the high voltage workbench because I have to play with some high voltage. Now, before we pop over to the high voltage bench and put something together, let's have a closer look at the schematic for the next circuit we're going to look at, which is a decimal counter assembly. Now, in the last demo, I already built out the 4 flip-flops, 1, 2, 3, and 4. And the other part of this assembly are 4, 1, 2, 3, and 4 pairs of neon bulbs. So what's going to happen in this circuit is when one of our flip-flops is high, the transistor will hold a 20-volt charge on the neon bulb, which will light up. On the other side of the flip-flop, the voltage will be about -10 volts, and that's enough to turn the other neon bulb off. Now that that is all cleared up, let's head to the bench and put this together. So here we are at the high voltage bench. I've got 3 power rails set up, a 10-volt rail, a 20-volt rail, and my high voltage coming out of here, my old Heathkit vacuum tube power supply, giving me voltage to light up these lamps. Of course, this guillotine switch, which has been in the family for years, is basically just showing me, demonstrating what the transistors will do. I don't really have the right transistors or the time to set it the transistors to fire from that flip-flop circuit to go into this, so this will have to do. So we start in the state where this neon bulb is on, and the voltage coming in this side is 19 volts, and the voltage coming in that side is 10 volts. Therefore it's a thing. So when I do the flip, and the flip-flop goes the other way, this time there's 20 volts there, and about 10 volts there. So it flip-flops back and forth. That's basically all she does. And of course that way is how they could drive those Nixie tubes using just simple transistors. They're really only playing with 20 volts here, positive and negative, rather than the 100 plus volts to drive these Nixie tubes over here. So like I just said, I can't really create the next circuit on a breadboard, but I can make a nice little animation on how it really works. So what I'm creating here is the actual Nixie tube driver. Back when they were putting this counter together, they did have transistors that could drive the high voltage of a Nixie tube, but they were expensive, power hungry, and too large for the compact design the engineers wanted to build. They might not have had the correct transistors, but what they did have was photoresistors. Let's start off with our 8 neon bulbs all neatly in a row. As we saw in that last demo circuit, there are 2 bulbs for each bit. The orange one for on, marked with a letter, and the red one for off, marked with a letter with a line on top for off. Now, of course, the neon bulbs don't actually have a color, they're just white neon bulbs, but it's easier to understand it when I give them a color in this diagram. So we'll start with all the bits on. Now, as I mentioned before, all the bits are given a weighted value. The A bit is a 1, the B bit is a 2, the C bit is also a 2, and the D bit is a 4. Add all those up, of course, and you get 9. Now, those familiar with modern 4-bit integers might figure this weighting is a little bit off. But given that the engineers who were building this counter only needed to count from 0 to 9, there was no need for any higher binary numbers. The circuit will start off, of course, with our 8 neon bulbs, and then we'll just add in a circuit board, and that circuit board is going to have a power supply for the Nixie tube, and then of course we add in our Nixie tube. Next is our negative potential that's going to be controlled by the neon bulbs. Now our first bit is high, so the photoresistor for the first bit high is going to allow current to pass. Next, B is high, and we have a photoresistor that lets current pass through that one, which of course leads to the next photoresistor, which in this case is D, which will start conducting, and the output from that is connected to the pin on the Nixie tube that will light up number 9. And I'm not going to walk through all of them, but I'll take one as an example. We'll use number 5, and the more astute of you out there might say, well, wait a second, with A, B, and C on, aren't we going to have more than one path to a Nixie tube digit? As with digit 9, we have our A positive resistor letting current through up to the B positive resistor. Now to continue to a digit from this point, either C negative has to be on or D positive has to be on. And since we're not in that state, nothing further is going to happen down this line. Carrying on along in the circuit, we get to the A negative, which is not going to conduct any current. So then we go to the C positive resistor, which will start conducting, which will go to the D negative resistor, which will start conducting, and then back into the A positive resistor, which is already conducting, and that's going to turn on digit 5. So that's how the whole system works. You can even set this little animation up to just go in a running loop like this. Almost hypnotic. Anyway, let's get back to repairing my counter. I think I'm just about ready to tear it all apart. Okay, now that we're done all the edumacation stuff, or you've skipped past all that crap, we've come to what a lot of people think is the fun part, and that's actually opening the puppy up. Now this is the first time I'm doing this, so I'm seeing this for the first time like you are.
Okay.
Alright, now, one thing and one of the guys at the radio club told me, when you're dealing with these old early transistor stuff, it's a good idea to keep a pair of clean gloves so you don't get any messy fingerprints in it. Because sometimes the old circuit boards are very sensitive to finger goo. Yeah. Okay. They look like the correct screws. The one looks correct, two look okay. Alright, let's see what we got going here. That comes off easy enough. Whoa! That am sweet. It's clean on the inside. A little dirt here. Yeah, this is why. You see that stuff here, the old rubber, the old foam? It's actually toxic once it gets to that state. So we'll have to clean that up and get rid of the phone. It's also, this is zinc chromate on here, which is zinc chromate paint. You don't want to get that on your fingers, because if you get that in your eyes, you'll know it. Good idea to wear gloves. It's nice and clean anyway. Did they ever make these things nice? So we can zoom in a little here and have a quick look. Let's have a look over at the power supply before I take anything out. Pokey stick. So just looking at the power supply, the caps are there. You don't see any leaking in there. It's a big ass transformer. Everything looks to be hooked up correctly. Fan is there. Spins. Switch is there. It looks in really, really, really good shape. Now to start disassembling it. Again, I want to take all the cards out and clean them. Ugh. I don't see anything that is too bad. You can see at this stage in the game, there's a 1 microfarad 200 volt cap there. So they were getting these big tubular caps at this time. That's why we wanted to check for leakage. A few big ass resistors here, or those capacitors, hard to tell. See when we take it out. That's the power supply here, I think. So, could be a tantalum there. Of course, all sorts of transistors everywhere. The power transistors are over here in the back. We'll test those as well before we do anything else. Hey, I think we can start lifting boards, and according to the instructions, you lift the boards this way. Got to take off that bar to get at the Nixie tubes and take those out. And there's that one to take out too, which is the, I don't know what that is. But anyway, now we can start playing. I don't think there's any need to take the bottom off as of yet. We can do that after we get the cards out. Start taking this apart. Now, there's no need to take the attenuators and the switches out. They're all in pretty good shape. But I'll start over here with this board. I think we just pull straight out. There we go. So what's this one? There it is. And it's a Series 413 615 Rev B, but no identification on it. Inside it says A5. A5. I have to look up what A5 is. So A5 is in there. I have my list of assemblies. A5. You know what this is? This is a differential op amp. Of course, nowadays we just see any jelly bean op amp. But this is what an op amp would look like if you had one on a circuit board. You can zoom in on that. Look at that. What a beauty. It seems pretty dirty down there. Yeah. Needs a good cleaning. So, okay, so now that I have the board pulled, the first thing I'm going to do is mark it with a sticker so I know what the hell it is, as it's not marked on the board itself. A5. And then I'm going to go right there. See, nice sticker, A5. Double check, A5. I'll put it away. Let's take out this one. Probably A6. Yep, A6. Again, dirty there. That's a, oops, sorry. Again, it's just dirty on it. No, wide out a bit. Wide out a bit. Again, it's just dirty. Zoom in there. Focus. Yeah, again, dirty, dirty, dirty. All right, keep them going. Next little baby. A7. And this should be A8, and that would be the other trigger assembly. It's even got the OR gate marked. Oh, look at those transistors. Raython. Again, dirty as all spit. Double check what it says back here. Hey, ooh! Just noticed we have a bug in it. Let me get back to that. Okay, I have to show you this bug I just found. Our first fault. Oh, not sure I'm going to do this. Zoom in here. Zoom, 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 zoom. So we're going to fix our first bug. Where are we? I'll zoom out a bit. Focus. There, it's our first bug. Take that little guy out of there. Yeah. There you go. That's an easy bug to fix. Where is he? There he is. A little arthropod. No, that's what it is. Not a gastropod. It's a arthropod. It's actually a sea creature living on air. Anyway, we'll go into my biology background. Oh, it's another tweet. There we go. And I bet you that's the power supply assembly. Revision A. Revision A. A1. How about that? Oh, nicely marked up. So, there's our two adjusting pots. That trend. What is that? That is a 5 meg, a little burn there. We have to do a test of all. Anyway, you can see that's a little burn there, or a little heat. There's one electrolytic on there, some diodes, they all should be okay. A couple of 47 picofarads, there's nothing special about those. I have to check these resistors for tolerance. That is 4 watts, 2 to 4 ohms, 5%. Or 2.4 ohms, 39 ohms. What does it say? 4 watts. Can't see on that one. Have to look it up. Anyway, I have to check those resistors. I've seen some use. You can see it's a little darkened around the corners there. No, don't put that one away. What do you bet this one's A2? There we go. No, that's A26. According to that. What's A26? Sample rate control assembly. Cool. Yeah, that one's in nice clean condition. So A26. Alright, put the sticker on that one. Okay. To be careful, here's my Nixie tubes. There we go. Simple enough. There we go. And that would be my Nixie tube in there. Nice little guy. Okay, and what would that be? That would be A24, which would be decimal counter. That's my millions. Never see more than a 2, so that one's probably got 2 and 1 burned in. There's our flip-flops. And there would be the, hidden in there, and I could open it up now, would be the little neon bulbs and the light resistors, so whatever they call it, light emitting resistors, that would control that. So this is our flip-flops, I think. Yep, so there's one flip-flop there, very similar to what I created. But of course it's picofarads, where I was using other things. Anyway, alright, go put that one away. Oop, mark it first. A24.
Okay, let's get to... Let's stand up like that. This tells me to show. Just goes on like this. Remember where it goes. Can I do it now? Ah, yeah. Nope, I'll leave it in for now. Okay, A23, this is going to be rather systematic. A22. Well, I bet this is A21. Yep. A20. Stand up for causes any trouble. A19.
Let's see what we got here. Oh, not bad for being in there for 70 years or 60 years. A25. Which one's that? The gate control assembly. So that is our Schmidt trigger. That's a, is that a transistor? Yeah, transistor there, transistor, transistor, transistor. Some neon bulbs it uses for the gate. Cool. That is cool. I guess one bulb's on, one bulb's out. That's the gate controlled by the multi-vibrator. Or is that the Schmidt trigger? No, that would be the multi-vibrator controlling the gate. I think. I'll have to go check that. One more off the main board here. What is this guy? Okay. Which would be... decade divider. Oh yeah, 1, 2, 3, 4, 5, 6. 6 of those. Okay. You have to be careful. A16. Anything holding that one down? No. A15. Good. Again, this is another flip-flop. I think that's a flip-flop. Decade divider? I have to check that one out. I didn't do a flip-flop, but it's definitely a flip-flop there and a flip-flop there. Here, flip-flop, there, flip-flop, everywhere, flip-flop. The nice thing is all these cards are swappable.
Always makes sense. Next one's A13. Oh, we have should be next, that's A10. Will be another decade divider, but that doesn't look like an A10.
Decade divider. Yeah, so it's much smaller transistors on this one. Must be a different revision. Does it say a different revision? 6009, so I think it's a different revision. We'll have to look at it closer later. But you know, okay. I bet this one's A9. A9. The A9 is the good old oscillator. Ooh, domino cap. Yeah, we still use them even up in the 1970s, 1960s. You see that in my old radios. I like that big 200 volt 1 UF cap. Huge. That must be very precise. Look at the hand wound inductors there, it looks like, or something. I'll have to go through the schematic on that one. Anyway, cool. A9. I'll come out. What is this one? Right over here. It does say it's an OR gate. It's an OR gate. It doesn't say what it is. Must be part of the time base, unfortunately. Alright.
That one to the side. Oh, they just marked that one.
Ah, there's our little decimal assembly. 1, 2, 3, 4. Cool. Love the neon bulbs. So I really have no idea what these two are. I'll have to go look it up in the schematic. So ran upstairs, printed off the locator for these two ones, and as I thought, this one is the A18, which would be the decimal counter, obviously, because there's the decimals. That to the side, so that's A18. A18. Oh yeah, includes main gate and measurement language units. Yeah, so that's it. It just reads funny. And the next one looks like it should be A17, which is the time-based divider. Includes printer hold-off amplifier. Interesting little card. And that's all the stuff I can take out. I'm not going to take out the decimal point assembly for now, which is this one down here, but I'll get to that later. Step 2 on the process is to inspect everything closely and see what's going on. See if I have any obvious errors or breaks or stuff like that, and do a little cleaning here, get rid of all that. And let me go full commando here for a few seconds.
We'll see the fruit of my labor.
So I've taken all the boards and laid them out on this table, as you can see here. And you know, there's no other better word for it than calling this discrete component ponography. It's just built so neatly. You just don't see this these days. Well, actually, you'd never see it anyway. Didn't see it much in the old days either. Very short term in actual components. You know, ICs came out very quickly after these things were built. Anyway, onwards and upwards to the next part of my list. Yep. Well, I think I've droned on enough for one day. I guess in the next video I'm just going to keep carrying on with my list. Give everything a good inspection, fix anything I find wrong, reform my caps, and maybe put it all back together. I think Gunny can take us up now with that nice little animation playing in the background. See you all in the next episode.